Hi, Andrew.
Hi, Sword. I can hear you well.
You can hear me?
Yes.
Fine. And what is the procedure? I cannot recall. I will just share my screen when it's my turn.
Yes, exactly.
Okay, perfect. Perfect.
And Tice will introduce this morning.
Yeah.
Hello, hello. Can you hear me?
Yes, I can. Morning, Maya.
Excellent. Thanks.
Yes, loud and clear.
Great. And thanks so much, Thijs. I really appreciate it.
Yes, of course.
Thijs, do you want to take? Oh, go ahead.
Go ahead, Amber. No.
I was just going to ask if you wanted to take over screen sharing the intro slides.
Yeah, I'll do that. I was about to comment something on Maya's picture.
Yeah, that's not me, and I can't find one to change it for. That's my husband.
Yeah.
I had to change computers, so.
Well, it's 1 minute to the hour, but I think we will slowly get started. I'm Thijs Lange, and I have the honor of taking over as moderator from Maya. Maya is here, but on a connection which does not, maybe not completely support video. So I got the honors instead. That said, I would just like to welcome all of you to the second installation of the spring webinar series on the within the Joint Initiative for Causal Inference. We call that the Joint Initiative for Causal Inference. It's a collaboration between UC Berkeley, Novo Nordisk, and University of Copenhagen. And the vision is to increase and expand the use of data for evidence generation. So not just more data for ever more sort of associational studies, but trying to get to the causes and using the methods of causal inference. In particular, we would do that through the expand the knowledge and practice of causal inference, not least through the causal roadmap and the whole machinery that is being developed along those lines. And the ultimate objectives is to engage outside of the kind of institutions present. In some sense, of course, these initiatives are running the risk of preaching for the choir. Most of us have seen the light about causal inference and those approaches to our field, but the joint initiative wants to move beyond that and get regulatory agencies, other researchers, the public at large, more involved in these methods and the way you can and cannot use observational data. Clearly, that also means develop software that should support the use of causal roadmap principles, tutorials, etc., etc. So the session for today is on mediation in broad terms. I will have the pleasure of starting with a story about how are epidemiologists working with current mediation tools. So a couple of stories from my experience. We're working as a consultant, collaborator with a bunch of people on applied mediation projects. Then Dr. Søren Rasmussen will present a Novo Nordisk-led mediation analysis. on sort of a somewhat more complex mediation analysis, but based on really good data. Then Dr. Zhe Wang will present some methodological advances in targeted learning applied to longitudinal mediation analysis. And then we have a Q&A session at the end. Just so you all get the sort of structure, then we will be moving from somewhat of a descriptive of what is actually done out there through some cases leading to what are the right here and now contributions to mediation analysis that we are trying to do within the joint initiative. So for the Q&A format, please type in your questions into the Zoom chat or at the chat at YouTube if you're watching it on YouTube. Then at the end after the 3 talks, we will have a moderated Q&A session. Questions we don't address within the time, we will return to. Oh, I think I want to do a little bit of advertising as well. On May 5th, we have the 3rd session, which will be an overview of methods for the integration of observational and randomized controlled trial data. And on June 2nd, we will try to highlight applications of the causal inference roadmap to dementia using Danish health register data and fused with RCT data. Okay, so that will bring me to my own presentation. So we do like that, and we do like this, and we do like that. And I am planning to spend something like 20 minutes on this talk. We'll see how it goes. So why do epidemiologists like mediation analysis? They really they like it because it promises a way to understand or learn causal mechanisms behind observed relations. And that, at least for quite a few of the epidemiologists I'm working with, this is exactly the holy grail. They want to understand what actually creates the kind of associations we see in data. So there's been quite a lot of hype within the EP community about mediation analysis. Maybe it's coming down a little bit now because a more realistic people are maybe being a little bit more realistic about what can actually be delivered and what kind of data do we actually have. It also, mediation analysis promises to quantify known causal pathways or maybe even refute that they exist, sort of Popper's approach. And as a completely different thing, it is also viewed as we can do a mediation analysis to identify targets for future interventions. If you are well into the literature, you will see not all of these, or in mediation analysis, you will see not all of these goals are actually necessarily perfectly addressed by mediation analysis. So that's actually also part of the process that's going on now. What can mediation analysis do, and when should we actually do something completely different? What is my data for these assessments? Well, I have been involved in quite a number of applied mediation projects, and it's from social AP to intervention research to psychology, intensive care. In short, anecdotal and very, very, very much biased towards what goes on research-wise in Denmark. That's the called reservation. So I will go through two cases. In question form, they are hospitals treating people of different social backgrounds equally well? And the second question, what is the role of adherence to secondary treatment among heart patients? Both of them are not old, but it's not bleeding edge research. They've been published a couple of years ago, but I think they highlight some interesting aspects that I would like to bring forward. So the first one, hospitals treating people equally well. It was a study that was commissioned by Rigsrevisionen. So that is in the US terms, I believe that is the equivalent of the Congressional Budget Office. And one of the ideas in the Danish healthcare system is that no matter your social background, you get the same kind of care. The Rigsrevision, they asked this study to be made, and there were a couple of environments that offered to do it. Rigsrevision selected a group from Aalborg University, which is like number 4 city in Denmark. They were all AP researchers, and they asked me along as sort of a mediation person. The kind of data we have, it's patients treated in the period from 2007 to 2016. It is very, very far from all patients. It is what we chose to, what they chose to do, was to say, let's focus on some specific diagnosis where there is a well-defined packaged treatment. So the idea being, for a couple of diseases in Denmark, if you get that diagnosed, it should automatically activate a whole bunch of treatment choices, treatments, and the degree to which these are being activated is a measure of, are we providing the quality we should? So the problem here, of course, is that establishing that people with low socioeconomic status die faster, have poorer health outcomes. That's, of course, a problem, but it is not necessarily an argument for that the healthcare system is failing. It could simply be that the people are more sick when they enter the hospital, and well, it cannot be the hospital's job to fix all. It's not possible for the hospital to fix all everything that's wrong in the hospital, in the society at large. So this is where the mediation analysis comes into play. The idea being that we have pretty standardized patient, if such a thing exists, with a lot of data. Because we have even more data than in the quality in the Danish registers, because they become patients now. So we have the opportunity to ask them stuff. So we would have patients diagnosed with one of these standard diseases. We would have data on their age, comorbidity, gender, income, previous income, education, alcohol, smoking, previous healthcare uses, etc., etc. Then we have the potential mediator was, did they receive treatment according to the predefined package? So there was a whole bunch of questions there. Did they get, were they offered that kind of medication within that time window? Were they offered surgery within that kind of time window, or was it not relevant? Etc., etc., etc. So we have this sort of quality type, somewhat high dimensional, multi-dimensional at least mediator, and then we have an outcome that would be 30-day mortality. What are the technical challenges here? The first thing one notice is that the mediator is at least multi-dimensional. I would call it as being 10-dimensional, but I'm slightly in doubt, but it's in that order, around a 10-dimensional mediator. That would take some standard methods of doing mediation analysis that they could no longer be applied, because they simply cannot accept a multi-dimensional mediator. And already here you see how it's actually being done sort of in real life among the epidemiologists I work with. We sort of start with, oh, this is in very rough terms the kind of data, the kind of question we want to answer. This is our data. Over here we have a bunch of potential tools for doing a mediation analysis, and now we start to strike them off if they for some reason don't work, and then we see what we're left with. It's not a perfect approach, right? Because it has this, well, we will just force the problem down in the tool that is least bad for that problem. The high dimensional mediator case is is actually very, very well solved by the R package Medflex. That part it handles really, really, really well. Next problem was there's a somewhat unclear definition of exposure. One could, of course, say, let's say high education versus low education. But that is a poor measure of social inequality. They actually solved it by it's an alternative approach, and it took me some time to get used to it, but I actually think it makes sense. So what they did was they took the first couple of years, then they looked at outcome, they looked at mortality, and they said, given all we know about social background, what predicts who comes out top and who comes out low? Let's use that model to construct a classification, and then we take that measure and use it to the rest of the sample. And for the mediation analysis is then only done on the rest of the sample. So what you're doing is that you're making a function informed by the first data that reduces a high dimensional exposure like variable down to a high versus low, high need versus low need. I insisted that we also try to do the analysis simply with education, and they give similar results, if not as striking. The effects are not so big. There is an unclear question about, is the causal effect of exposure actually meaningfully? We cannot really intervene on it. So is the whole setup the right one? Here, I actually think that we are in a case where the natural indirect effect is actually the right one, and it was used very explicit in the report to the government, or its parliament, report to parliament, namely what kind of mortality would have been observed if the group with the highest need had been given treatment as they do in the group with that is a high social class. You could call it natural indirect effect, or you could make one assumption less and call it a stochastic intervention. I think that it was mostly read, even if it was not written explicitly like that, as trying to quantify a stochastic intervention. Then the full data is actually a survival outcome, which would have complicated things further. Here we restricted to 30-day survival. I actually think that's a better analysis, because we wanted to measure what is the contribution of the healthcare system. If we had gone into survival analysis, we would have mixed it up with secondary treatment, assisted living homes. Are they equally well distributed across social classes? That would have been a problem. How was this presented to Parliament? This was a high need versus low need comparison on odds ratios terms. So the total effect was something like an odds ratio of 23. The direct effect was 18, yielding around a 30%. 30% of social inequality is created in the hospital. That was then the final conclusion. So some questions and reflections based on that. Maybe we should start with, is this odds ratio really a relevant effect measure? And much worse, what are the 20% a percentage of? Here we put in we made the highest possible contrast. But should or shouldn't you take, for instance, social, if you have diseases, lifestyle diseases, as a result of social class that are pre-existing, should they be factored in as part of the social gradient? That is what we did here. We sort of tried to maximize it. Or should they not? Should they simply be controlled away? The indirect effect would stay roughly similar, but the direct effect can vary greatly depending on how you define it. And surprise, surprise, the thing that mattered for the policy discussion afterwards was this 23%, a quarter of social inequality is created within the hospital. Depending on rather technical choices in the mediation analysis, that number could have ended up a completely different place. Then an observation that the Rigsrevision found mediation analysis hard to understand. It seems still to be a problem. How do we communicate this in a way that doesn't seem so complicated, so contrived somehow? And then a more technical problem that appeared and was never really, I think, addressed. That is that a number of these diseases, they are not like a broken leg. They do require that you get diagnosed with them. And there could be a timing issue here. And that has sort of multiple effects, because if you define the social gradient on survival as sort of high as possible, then late diagnosis affected by social class will pop in as part of the effect of social class. But not only the measurement, but also the definition of the mediator is itself affected by this timing issue. It could or could not be an issue, but it does suggest that the whole longitudinal mediation analysis is something we need to think about. Then I have my case 2, which I will go through a little bit more briefly. So this is about acute coronary syndrome, and the original study was to establish what is the best treatment strategy sort of when you register this. Very, very much simplified. There was 2 strategies. Either you, as soon as you have people in the ambulance, you take them to the heart center and you go in early invasive, you treat aggressively at a specialized unit. The alternative would be a little bit, not exactly careful waiting, but taking patients to a more local hospital, only going invasive, only transferring them if the situation deteriorates. Which of these treatment strategies work the best? We did a large observational study. There was some instruments that some instrumental variables techniques and some other issues like that. And at the end of the day, we found out that a hazard ratio for early invasive versus usual was an 0.7, so a pretty strong reduction. Again, about the causal roadmap, is this the best effect measure? Could anybody really interpret this effect measure? I'm not 100% sure, but this is the kind of world, of course, we are up against, that this is so customary that this is what we are expected to do. The next question was to sort of dig one step deeper and remember my intro about epidemiologists like to use mediation analysis to understand mechanisms. That is, what was the role of secondary preventive treatment? Was it such that this reduction we saw was actually partly mediated by that getting the patients to these specialized centers also informed them better, made them more aware that they actually had to take this medication? And again, it was relatively easy to do because there is a well-defined package of medication you have to take. So we could simply look up in the prescription registers, did they take it? A technical challenge here was a couple of them, was first a conceptual one that if people die, they can't take secondary treatment. So how should that be handled? Here, we actually chose to condition on surviving 30 days. And because that would allow us time enough to have a measurement of did you take out your prescribed medication in that time period, and then use that as a mediator for whoever in the population of whoever is left moving forward in time. I am in this room full of causal inference experts, not claiming that there are not issues with this approach. There are some weird conditionings going on. But I'm trying to highlight that these kind of questions and these kinds of hacks to solve them is what is being done out there, even though clearly one could have thought about this taking out secondary preventive medication as one of these longitudinal processes. But the framework, the tools were not there. So I will not go into all this code. I included it because for reference it can be useful, and maybe as a little bit of a sales pitch for the Netflix, because once you have this DAG, so with a with this multi-dimensional 4-dimensional mediator, a whole bunch of baseline covariates, and a well-defined binary exposure, then assuming you were only looking at a binary outcome, so for instance 1-year mortality, you could do the whole mediation analysis as it is now in 3 lines of code. Okay, this is more than 3 lines, but that's because there are many control variables. Really what goes on is just that you fit a logistic regression to the outcome, including everything. This is sort of an auxiliary model. You feed that into, so including mediators, exposure, confounders, everything. You feed that into this NE impute function, specify the number of mediators. Then you make a final natural effect model, as I like to call it, where you look at the outcome, and then you can directly, using usual regression technique, have a coefficient for the natural direct effect and one for the natural indirect effect. And you run it. So that was the 3 lines of code. And in this case, we got a odds ratio scale, 0.55, natural indirect effect of 0.84, and a natural direct effect of 0.66, together yielding a mediation proportion of 0.3. This indicates again that if we want to provide something that is going to be broadly used, the level of complexity needs to be something that is roughly comparable to this. There are alternative software packages out there, the Causal Med package for SAS, or the procedure for SAS, mediation package, M+, and so on and so forth. They are not perfect, but they are relatively simple, and they do get you quite some distance. So I think we need to have that at the back of our mind when we address these, when we look forward. I had a couple of more slides here where I show that you could also do this analysis with a proper survival outcome. It requires a little bit of a hack. Interestingly enough, if you do a natural effects Cox model instead of the 1-year survival model, then the estimates of effects are not that close, but the mediated proportion is quite close. That's an observation that I have seen countless times. It obviously cannot be a proper mathematical result, but in practically all settings I've seen, the mediated proportion is surprisingly robust towards the kind of methodology you apply and the scale and so on. As long as something meaningfully can be defined as a mediated proportion, it all often stays fairly constant. So in conclusion, this last example, is this a case of a square peg and a round hole? To a degree, yes. There were definitely made analytical choices in order to make it fit into the software. So that is what's going on. It's also a case of that these more sort of computer technical issues, like what is the dimensionality of the mediator? Are we talking about a survival outcome or a binary outcome? Those kind of issues, they end up taking up quite a lot of resources when you do these mediation analysis sort of in real life. All right. This actually wraps up what I had planned to say. Remember, there will be a Q&A session at the end of the whole talks. But for now, I would like to invite Søren to present his work. So I guess I will stop sharing.
Yeah, many thanks, Thijs. I will try to share my presentation.
Looks like it's working.
Yeah. Can you see my presentation in full screen mode?
Even in full screen, yes.
Thank you. That's nice. Yeah. Many thanks for this opportunity to speak about mediation using the LEADER data. And I should say that this talk is made in collaboration with my colleague Jesper Madsen here at Novo Nordisk and our former colleague Martin Linder, which is also author of some of the papers presented in this talk. He has also made some of the slides which I have copied. So we will now move to, you can say, a more controlled world as opposed to what Thijs presented, namely randomized trials. And in 2016, the results from the LEADER trial with almost 10,000 patients randomized was published. Originally, it was a non-inferiority trial, but LEADER, which is the compound studied in the trial, was also superior for the primary outcome. This, of course, prompted the question, what is the mode of action for the cardiovascular risk reduction? For some, it can sound strange that the biological pathways cannot be explained fully, but this is actually a question that also nags other sponsors in cardiovascular risk reduction in type 2 diabetes patients. We will see some of these publications addressing this mode of action later on in this talk. Now, a way of addressing this mode of action question is mediation analysis. Actually, in 2016, when LEADER was reporting the results, I did not know what it actually was when a colleague of mine suggested we should do some mediation analysis, even if the concept was introduced in this famous paper by Barron and Kenny almost 30 years earlier. You can say that in my defense of, should we say, ignorance, I can maybe argue that the development of this topic has been particularly intense in the last decade with a root or origin in causal inference using the counterfactual framework, also to overcome the problems there is with mediation in nonlinear models as in Cox regression. Furthermore, the focus of using mediation analysis in randomized trials have also been intensified by regulators and academia. On this slide, GLP-1 works to a lot of potential pathways that could be cardiovascular protection by some anti-inflammatory properties, both affecting the heart and brain, but also through the pancreas and the GI tract, where the former two are, of course, interesting from a cardiovascular risk perspective. Just a quick glance on the LEADER trial design, 9,340 subjects randomized with LEADER as the GLP-1 compound versus placebo added to standard of care. You should know that the potential mediator variables, for example, from lab measurements and vital signs, are measured at each trial visit, where for some measurements there could be 1 year between. The primary outcome in LEADER was MACE, which is a composite of non-fatal myocardial infarction, non-fatal stroke, and CV death. There was a 13% risk reduction, showing superiority for LAIA versus placebo. Hence, there is a relationship between treatment and the outcome of interest, which of course is a prerequisite for mediation analysis. Now we turn our attention to potential mediators. As GLP-1 foremost was developed to reduce blood sugar in type 2 diabetes patients, it is no surprise that LAIA reduces A1C across the trial with a quite fast effect in the first months. At 3 years, there is a difference of 0.4% between the two arms. Other lab measurements and vital signs could also be of interest, but we focus on these 4 potential candidates. A1C from the previous slide, and here change in body weight, albumin creatinine ratio, and systolic blood pressure in this talk, all of which is significantly reduced for LAIA versus placebo across the trial. These 4 variables are the 4 highest ranking variables based on set scores in a mixed model. Reduction in A1C has been in focus as an explanation of the cardiovascular benefit in the outcome trials. Indeed, this meta-analysis, we have reduction in A1C from baseline at the x-axis and the hazard ratio of the primary outcome between the active compound, that is DPP-4, SGLT2, and GLP-1, as you can see on the right side, in the various huge cardiovascular outcome trials. SGLT2 and DPP-4 reduces also A1C, like GLP-1 in type 2 patients. There seems to be a relationship on these aggregated data for GLP-1, but not for SGLT2. That at least was the authors conclude. You can see the 2 other CVOTs from Novo Nordisk in the ends of this plot, that is Pioneer 6 and Sustain 6, which includes another GLP-1 called semaglutide as all and once weekly injection versus placebo, but in the same cardiovascular risk population as in LEADER. Pioneer 6 and Sustain 6 randomized approximately 3,000 patients, and the trial duration was just about 1 year and 2 years respectively. Hence, the number of MACE events were much lower than in LEADER, with the median follow-up of 3.8 years, as you can see on the confidence intervals for Pioneer 6 and Sustain 6. And you should, of course, note that one of the many weaknesses of these kind of analyses is that A1C reduction is taken at different time points, partly due to the difference in the follow-up time at the different trials. Also, in this slide, you can see the results for the Inference trial, and you can see the results for the Inference trial, which also has done mediation analysis in this field. And we will come back to that now, because in this slide, you can see 2 publications, one from Empiric and one from Rewind. Because you can now ask the question, how should you analyze these kind of data in a proper way, leaving meta-analysis behind? In Empiric, you can see here, there is they reported a risk reduction in CV deaths of 38%, and hence the sponsor here was interested in the analysis potential mediators for this endpoint, and also results from the Rewind that was in 2020, last year, with another GLP-1 compound called dulaglutide, which is also a 1-weekly injection. And they also published potential mediators with MACE as an outcome. And what they do in these papers or abstract is that they are looking at time-dependent Cox regression as the approach of analyzing mediation, which you can see on this slide. Hence, you can estimate the total effect, which is simply the treatment effect on the primary outcome, the sum of the direct and the indirect effect, and then the indirect effect, that is the effect from treatment to the mediator to the outcome, as you can see on the diagram on the left side. Hence, the direct effect would be how much the treatment effect is actually attenuated towards neutrality in the time-dependent Cox regression. The proportion mediated can then be calculated on the log scale using the last two formulas on the right side. All of you who has analyzed data with time-dependent Cox regression, they know how the overwhelming number of possibilities these time-dependent variables can follow with a measurement at each trial visit. Should it be change from baseline? Should it be area under the curve, approximating some kind of cumulative effect of the mediator? Should it be a lag effect, etc., etc.? But what has been chosen here is two time-dependent approaches in the Cox regression, change from baseline at each visit and updated mean at each visit as time-dependent covariates, where updated mean is area under the curve, standardized with time. And at any given time point, the most recent observation of the mediator is used to evaluate the risk of an event at any given time point, and an average of all prior mediator values is used to evaluate the risk of an event. And both these methods, they were introduced in the MPAVAC mediation from the previous slide, and they say that the change sort of target, and you can say an instantaneous effect of the mediator variables, while the cumulative effect of the mediator variables is targeted by the updated mean. So if we now do the analysis for leader using this time-dependent approach in the Cox regression, and we look again at these four variables, mediator variables mentioned before, we can see that A1C and albumin creatinine ratio contributes most to the proportion mediated, with approximately 41% and 29% respectively. Body weight does not contribute at all, with a negative mediation using the time-dependent Cox regression, and the mediation for systolic blood pressure was modest. The Rewind trial on the previous slide reported that A1C mediated 36% for MACE using the updated mean approach. Hence, the result for A1C in relation to MACE is in accordance for leader and Rewind. So, but there is, of course, some limitations of this time-dependent Cox regression approach. As previously suggested, a single summary cannot usually capture the full complexity of the mediator. This might lead to a weakening of the indirect effect. Such simplified mediation analysis, moreover, excludes satisfactory control for confounding. For example, the area under the curve measurements combine the repeated assessments of the mediator over time. This excludes adequate control for the confounding, because some of the covariate measurements measured during the study will then be both the cause and effect of the obtained area under the curve, which can be unwanted. Basing the analysis on the last recorded level of the mediator may appear to overcome this problem, but is also problematic. The reason is that the association between the last recorded level of the mediator and the time to event endpoint is confounded by previously recorded levels of the mediator. Furthermore, the last recorded level of the mediator may be influenced by the event time itself, thereby inducing problems of reverse causality. So, this call for an approach which entails the repeated nature of the mediators and confounders. And this is done by the authors of this paper, which is a collaboration between Novo Nordisk and Professor van Saland and colleagues from University of Ghent in Flanders. The following analysis is based on this method, and also the authors did actually develop a SAS program, which can be downloaded from the supplementary material attached to this paper in statistics and medicine. So, in this diagram, you can see how complex the implementation of repeated measures of mediators and confounders can be. M8 and M2, etc., is the mediator measured during the trial visit, and L8, L2, etc., is the confounders during trial. A is the randomized treatment, and I is the outcome. Sorry, T is the outcome. As you can see, due to the randomized treatment, there's no error from the baseline covariance L0 to A, as this is a randomized trial. What you should note from this diagram is that this new method entails that each time the mediator is measured, the model allows for a direct pathway between the repeated measures of the mediator and the outcome, and the same for the confounders. Hence, it circumvent the more naive approaches, as noted in the limitation. Also, this new approach originates using the counterfactual framework, and hence the interesting measure is to estimate the survival. And that is the probability to be event-free for the liar subjects if the mediator values changed to the levels that would have been seen had the subjects been on placebo. This is what we call S10, that is the counterfactual survival for liar patients. I will not touch upon, you can say, the underlying estimation procedure in more details, beside that it's based on a G-like formula using both logistic regression and Cox regression, updating S10, that is the counterfactual survival for liar patients at each visit. And details can, of course, be seen in the Statistics in Medicine paper. Hence, the direct effect at each chosen time point is calculated as the difference between the placebo survival and the counterfactual survival, and the indirect effect is then the difference between the liar survival and the counterfactual survival. And the sum, you can say, if you sum the two last formulas, then you get the total effect, and that becomes the difference between liar and placebo survival. So this method has been used in an applied paper using LEADER data, published in Diabetes Care with the steering committee members of the LEADER trial as co-authors, and that was published last year. If we look at A1C, we can see that there is quite some mediation going on during the trial, as the counterfactual survival for liar patients, S10, approaches the survival for placebo, called S00. At 3 years, there is an 82 proportion mediated using the fraction between the indirect effect divided by the total effect. It also stresses the new method's ability to summarize the mediation for the chosen mediation variable at fixed time points during the trial. In this case, as you can see, 1 year, 2 years, and 3 years. So, if we look closely on the variability of the total and direct effect, we see using Bootstrap with 1,000 samples that there is quite some variability in the direct effect and indirect effect, and especially in the proportion mediated requires large confidence as well, which of course stresses the caution that should be taken in the conclusion of mediation from A1C and other mediator variables. But at least A1C is a potential candidate, as also the meta-analysis have suggested. So this slide is just a follow-up on the other 3 mediation variables. Albumin creatinine ratio with a proportion mediated of 33% at 3 years. Correspondingly, body weight and systolic blood pressure proportion mediated was 14% and 13% respectively. And you can see here the mediation is modest because the counterfactual survival for liar patients, that is S10, are very close to the survival for liar patients, that is S11. All these 3 mediators increased the proportion mediated as compared to the more naive methods, especially body weight, but there was this negative mediation. As also stressed before, the Van Stellaan method will also adjust for confounding variables in a proper way as repeated measures. For example, in the LEADER randomized treatment will Inference insulin use during the trial as an example we saw earlier in the diagram. Also, hypo events caused by low blood sugar could be a confounding factor with a relationship seen between MACE and severe hypo events in some observational studies. Adjusting for all the confounding factors mentioned in the title, including hypo events and insulin use, gives a proportion mediated by A1C of approximately 70%. So in close range of the 82% we saw unadjusted. So to summarize this talk briefly, Novo Nordisk has applied a novel method in mediation analysis using this counterfactual approach. These mediation analyses have identified A1C as a potential mediator of the CV effect or cardiovascular effects of liaglutide. Similar to all other mediation analyses, the result relies on the assumption that there is no unmeasured common cause to the effect of mediators and outcome. Generally, we see a higher proportion mediating using the Fenster-Land method compared to the more simple or naive methods presented, for example, the time-dependent Cox regression, which you can say then is in line with the theory about using repeated measures in adjusting for mediators. And also we see that results, they were quite robust when adjusting for various confounding. And last, we are at the moment pursuing mediation analysis in LEADER also, using LEADER data also in relation to kidney outcomes using the Fenster-Land method. Yes, this was my talk. Thank you for your time.
Thank you, Søren. There was a quick question in the chat. Maybe you could just answer that. Just to, in your words, what was the definition of the indirect effect again?
Yeah, I can.
On the, it was sort of on your survival curve.
Yeah, I can go back.
I should have asked before you unshared. Sorry about that.
Should I share again? I can do that.
If it's easy, yes. Otherwise, maybe just a few words.
I believe your slide 16 has the answer to the question.
Yeah. Just a moment. Can you see this?
Yeah, it's okay. It's okay. No need for the full screen.
Okay. So you can see here the natural direct effect that was surpassed as the counterfactual survival for LIAR patients minus the survival for placebo subjects. So if we go to this curve, you can see here the direct effect is then the difference between the lowest curve and the curve just above.
This was absolutely perfect. Thank you. Alrighty. Then we have the third and final speaker. This time, not a person at the end of the workday, but a person at the start of the workday, namely Dr. Zhe Wang from Berkeley, who will present methodological advances in targeted learning applied to longitudinal mediation and simulations, as well as applications to LEADER. So the floor is yours.
Yeah, thank you, Thijs and Søren, for the excellent introduction and presentations. I'm glad to be the next to further present on our work in progress with the targeted maximum likelihood estimation for longitudinal causal mediation. So this is a joint work with Lars Vanderland, Maya Peterson, and Mark Vanderland at UC Berkeley. So can start. Okay, so before we dive into any details of the longitudinal data and causal mediation, I think maybe we can start by introducing a bit about the big picture of the framework of TMLE statistical estimation. So say that we might be interested in some statistical target of inference. So that is itself a function of the data distribution. So some psi of P, where P is the data distribution. And in the most general scenario, we might just have our statistical model fully parameterized in terms of all the possible distribution, so which is demonstrated here in this plot. And here at the beginning, so we might start with some initial estimation Pn0 that is fully tailored towards our true data distribution P0, but with respect to some overall loss. Maybe that's the best we can do at the beginning, maybe with superlearner, with machine learning, with even deep learning. And then at the end of the TMLE update, what we really want there is that we want to solve the desired efficient estimating equation so that our TMLE update will be fully tailored towards our statistical target. So the idea here is that even if the TMLE update might be converging to our true distribution at the same rate as our initial estimation, with respect to the overall loss, our TMLE update might be a much better estimator for our statistical target. So meaning we can make it maximally efficient by incorporating machine learning and cross-validation based superlearner, and at the same time guarantee that is asymptotic linear and we can make valid inference. To apply this TME framework to actual specific causal inference questions, we'll need to first go through carefully, check out the procedure called the causal road mapping, where we need to specify our honest and true knowledge of our data structure and specify our actual causal question of interest and what are the assumptions needed to statistically identify those targets as our statistical targets in terms of so-called G computation formula. And starting from there, we might be able to let the TME take over. And if we indeed find out that this statistical target is pathwise differentiable with respect to some efficient influence function, we will be then able to transform some initial distribution estimate into a semi-parametrically efficient TME update. So for the rest of this presentation, we'll see how this general causal roadmap framework and the TME estimation procedure can be applied to the seemingly complex longitudinal causal mediation questions. And we'll also see how we can utilize the idea of computerized efficient estimation strategies to further reduce the computational cost and make our algorithm more stable and scalable. Okay, for causal mediation, also as mentioned in the previous presentations, we can start with point treatment setting where it is more thoroughly researched. So we have already many very reasonable causal targets to begin with. So our data structure here is very simple. We have only baseline covariance L0, mediator Z, intervention node A, and then the outcome Y. So the core idea of mediation is nothing but that we want to intervene the mediator node slightly differently. For example, with the controlled direct effects, we want to control our mediator node to a specific fixed level, small z. And they will want to see how much of the total effect can still be achieved when we do that control of the mediator. So that's why it's called a direct treatment effect when we strictly control our mediator. And there is also the idea of natural effects. So we intervene on our mediator with the control group intervention, even if when we consider the treatment group outcome. So in that way, we want to see how the mediator will behave naturally when they are in the control group, and see first how much of the total effect can still be achieved under that hypothetical trial. So that's called a natural direct effect. Or so this is the natural direct effect. Or when we fix our treatment level, so we don't consider the effect coming from comparing treated and control directly, but instead by the effect introduced by comparing the different impacts on our mediator, so to intervene on the mediator with treated or control regimes. So that's called the natural indirect effects. We'll also see that these natural effects will naturally just decompose our total effect. So it can be interpreted with the proportions of our effect that is mediated through the mechanism of this mediator pathway. So here I would like to introduce a very important idea called the random intervention. It will be very useful to identify the causal target of inference under the setting of longitudinal data. Is that we instead of intervening on the mediator to set at the specific level or specific counterfactual, we intervene on the distribution of the mediator directly and to let it behave as if they were in the control group. The reason we want to do that is that the traditional version we just discussed of the natural effects, it is known to not allow any confounder adjustment that are after the randomization. But for longitudinal mediation analysis, when the mediator itself is a process, that is something not even possible to achieve. So it is very, it will turn out to be very important for our problem setting. And we'll discuss the idea in the specific examples in the next few slides. And lastly, it's a small side note why TMLE might be important for this setting. Like we said, it's more like an observational study, even if the baseline treatment is fully randomized, because we are considering a manually defined hypothetical trial on the mediator, and also because of some possible informative censoring that can happen in the survival data. So it is really important to do as well as we can on the initial estimation, and also reflecting the true knowledge of data and still doing valid inference. So all these are the strengths of TMLE. Okay, so now let me start by defining the structural causal models for the very simple point treatment setting. So on the left-hand side, we have only the baseline covariate L0, intervention node A, mediator Z, and outcome Y. On the right-hand side, we add only one additional covariate that is after the randomization, so it's R. Comparing the static and random intervention, on the left-hand side, with this structure causal model, we can be very specific about what we mean by intervention and the counterfactuals. So we let the intervention node to be at a specific level, small a, and only for the mediator node, we let the level of intervention node to be different, so some a prime. So in that way, we defined static intervention, the traditional version of mediation target of interest. With random intervention, we intervene the mediator node differently by directly manipulate its distribution. So we make it as if they were the control group counterfactual. So in this slide, we can see that when we try to get identification results, first, when the assumptions needed are all met, they agree in the identified statistical targets. But then the traditional version will require one additional assumption. So that is called the cross-world ignorability assumption. So it is considered across two counterfactual worlds when we intervene the mediator and the other nodes differently. And this has been considered more problematic than other assumptions because this cannot be identified, cannot be tested, even if all the counterfactuals are observable. But more importantly, we'll see in the next slide, the traditional framework of natural effects will prevent us from identifying the causal target of interest in the longitudinal setting. Here is the simplest example to demonstrate that idea. We just add one more additional confounder R after the randomization. And again, we go through the same procedure of defining our static, either the static intervention version or the random intervention version. And we'll then see immediately our traditional version will fail to have a unique identification result for causal target of interest, but the random intervention version, because we directly intervene on its distribution, we can still get a statistical target as the G computation formula. So because of the fact that it's so important to adjust for the longitudinal time varying confounding, so we adopt the framework of random intervention. So this is our most general causal structural model. We still have the baseline covariance L0, but then for each time point t, we have our intervention node AT and then our mediator node ZT. But we also allow any other time varying covariance happen before or after the mediator node. And we can, so the outcome process will usually be included in the time varying node after the mediator. So all this flexibility will be very crucial if we want to justify our sequential ignorability assumptions, or when we want to maximally adjust for all these possible confoundings. Okay, here we give the identification result, the G computation formula for the mediation target. So we can see indeed we require no assumption about the cross-world ignorability. And indeed, our statistical target is now a function of true data distribution. So what we need to do next is just to work out its efficient influence function and then work out its TMLE update. Previously, so there has been a good amount of work putting a transformed version of this type of questions called a sequential regression. So the idea is that we, instead of working with the conditional densities, we sequentially define a sequence of conditional means and still end up with the same G computation formula. So by doing so, so the trade-off here is kind of, is an obvious trade-off that by working with conditional means, we avoid the density fitting if that can be problematic, and we avoid potentially computationally expensive analytic integrals in the influence functions. But on the other hand, we can, although we can still update them, but we'll use a technique called the minimum loss estimate. So it's a generalized, it's still TMLE, but generalized, so it might not be fully compatible with existing TMLE toolbox. And we will limit the type of causal targets we can work with. Like we have to be really focused on the conditional mean at the final endpoint outcome. And we also suspect that because of the nature of sequentially define these conditional means, we can see we define them starting from the last time point. We suspect that if we have too many missingness and censoring at later time points, which is usually the case in especially survival setting, the algorithm we suspect it can be a little bit unstable. And also recently there have been some new development on non-parametric estimation for density. So we think it's really a good time to come back and check out how well we can handle the numerical challenges on the other route with the density-based version. Okay, the gaps to be filled. So we want to develop some purely maximum likelihood-based TMLE. So we will work with density estimation and density update directly. We want to utilize the recently developed non-parametric density estimators. And we also want to use the computerized efficient inference function calculation to improve the scalability and stability of our algorithm. Okay. So given that the statistical target, now we want to calculate the efficient inference function. So first of all, we can already see that these type of questions tend to have a more complex expression in the inference function. So not only it has, for example, in the front, so it actually has a more complex generalized IPW term in the front. So it also has some complex integral terms and their differences. So we can already see part of the reason why this can be computationally expensive to calculate them and also use them in the TME update, and why if we can use some computerized idea to replace this analytical representation, we might be able to reduce computational cost. But another part of the issue here is that because of this special format of IPW scores, because of that, we'll have to rely on a very special set of positivity assumptions compared to other longitudinal data analysis and serial analysis. So in practice, for the finite sample positivity issue, we might be able to put some upper bound on these special IPW terms, or we can even do such bounding in a data adaptive way. But we will not go into details for that direction, but we will rather focus on how the computerized efficient inference function calculation can help us to partially avoid this type of issue. So we will have to define our TME update. So to define that, we will need to, for each likelihood factor involved in our G computation formula, we will need to define a least favorable path, so which is nothing but a univariate parametric model. So what we will do is that we will maximize our likelihood along this parametric path. And the idea is that because for the univariate parameter epsilon, when the epsilon equals to 0, the score of this parametric submodel will be the same as the desired corresponding part in the efficient inference function. So by maximizing the likelihood along this path, we will be approximately solving the desired efficient score equations. And we can formally prove that if we let the TME update to be the initial again and iterate all this procedure, we can show that the final TME update will converge to a solution of the desired efficient score equations. So here is the details of our iterative TME algorithm. And we show that the efficient estimating equation will be solved at a faster convergence rate. So one way to optimize and stabilize these update steps is to make these updating steps one step. So to achieve that, we will need to first put some modification on our the previously defined locally least favorable path. So now we want to define some universal least favorable path, meaning these new parametric submodels will not only match the desired score at epsilon equals to 0, but also match the desired score within an interval around 0. So that when we find the local maximum of the likelihood within that interval, we will just solve the actual square equation just in that one step. And what has also been shown is that this type of algorithm can be implemented in a very stable way, still using the locally least square path, but with the with the gradient descent style of searching. So we use very small step size in the local least square path update until we see that the log likelihood is plateaued. In this way, we can implement this one-step TMLE in a very stable way. So we have discussed about 2 ways that we can solve the estimating equation. The rest of the proof to show the asymptotic efficiency will be quite straightforward. We can always look at this type of exact expansion of our final TMA update. And then we can immediately see that to reach the desired optimal empirical process here, there will be only 3 terms that we'll have to control. So the first one, the first term here, the condition needed is just some Donsky class condition, which can be satisfied if we choose our initial estimator carefully, or it can be achieved by using some sample splitting techniques. So it's called the cross-validated TMLE. So it can be satisfied. And the second term is just the efficient estimating equation that we just solved. We can solve it to a fast converging term, or we can solve it exactly with the one-step TMLE. And lastly, there is a exact remainder term. So this is analytically defined. This term usually involves some cross products. And that's why this is usually where the multiple robustness happens. So for our problem here for the mediation, we have 3 sets of conditional densities for the treatment, for mediators, and for covariates. 2 of them being correct can guarantee the consistency of our final estimation. But again, as we said, we probably do not want to fully rely on this type of multiple robustness because the nature of the study is more like observational. So we actually suggest the use of algorithm like highly adaptive lasso for those density estimations so that we can have a guaranteed convergence rate just at the initial estimation so that we can have a guaranteed efficiency for our final TMIS update. Okay. So the last variation of our TME method for this problem is that, as we showed, the efficient inference function in this problem can be quite complex and quite expensive to calculate and to use them in updates. So we want to maybe at least partially computerize it, the calculation of it. So to do that, we noticed just one simple fact that the actual efficient inference function can be represented as a projection of the simple IPW inference function onto different tangent spaces. So as long as we can fit those projections good enough, and we will see that that won't hurt any of the 7 parametric properties of our final estimation. And more importantly, if we feed those projections with highly adaptive lasso, what we will end up with will be some very simple representation of the inference function as some linear combinations of a bunch of indicators or likelihood factor values. So those values can be easily updated whenever we actually update any of the likelihood factor. So what we can prove is that when we utilize this type of computerized technique, we'll have just one additional term when we solve the estimating equation, and this term can be well bounded if the projection is good enough. And what we'll gain at the same time, it will be some dramatic increase of the scalability of our algorithm. So next, let's move on to the simulation of the method we just discussed. For the simulation, we'll still use the setting in the Wen Jingzheng and Mark Vanderland's 2017 paper, and we still set the total number of time points to be 2, because we want to have a head-to-head comparison of the analytical version and the highly adaptive lasso projected version. From our simulation, we already know that with more time points, the analytical version can fail to run or take like hours to run, whereas the projected version will not have this type of issue. Okay. Okay, let's come back to the simulation. Okay, here's the first simulation setting where you have all the conditional densities correctly specified with logistic regression models. So all the estimators appear here should just perform fine. But we can see here is that what the TMLE will always do is that it decrease the bias and then it increase the estimation variance slightly. So that's how we achieve the bias variance trade-off for the final estimation. And what is very interesting here is that, so for example, with a smaller sample size, we saw some drop in the confidence interval coverage for the analytical version, which is we suspect might be due to the fact that we have to put some bounding on the IPW factors, which might have introduced some slight bias in the estimation of the influence function. But with the projected efficient influence function, we don't need to put any bound on the IPW scores because our projection algorithm, highly adaptive lasso, is quite stable and they can handle that type of instability issue just naturally. And at the same time, we can see the projected version still achieved a reasonable amount of bias reduction compared to the analytical version. And the second setting, very similar story. So in this setting, we misspecify our density estimation for L node and Y node for the outcome process by just using the sample mean. So the wrong estimator will just have a very small estimation variance, but also quite large bias. And we'll see the TMLE will achieve a very optimal bias variance trade-off. But again, the projected version tend to create a smaller jump in the estimation variance. So the next setting, we move away from the mediation questions to some just focus on the treatment group outcome level. So in that way, we can compare our algorithm, so which still works for this causal target. We can compare it with the sequential regression version of TMLE. What we found interesting here is that the general trend here, that the density-based estimators tend to give narrower confidence interval compared to the regression, sequential regression-based method. So which can be translated into potentially higher testing power. This might be because of the reason that this simulation setting, we have a quite severe censoring at the second time point. But so of course, we'll need more careful simulation and the simulation evidence to validate these ideas. And the other thing we also see is that the sequential regression tend to give a more aggressive, the most aggressive bias reduction because it's more focused, but at the same time, it makes the largest jump in the estimation variance. Okay, so the message here is that the projected version should be very promising here and also scalable for more time points. Okay, for the last few minutes, I will go through our causal road mapping part for the analysis of the leader trial data, which is part of the very exciting collaboration with Novo Nordisk and Copenhagen. So we don't. So we still need some work of getting the data sharing done, and we will hope to get the real data analysis result in the next couple of weeks. But for today, we'll focus on the causal road mapping part so that the TMLE estimation steps can naturally follow. So what is our general data structure? So we have the type 2 diabetes population from the leader trial inclusion-exclusion criteria. And then we assume this over 9,000 registered patients to be IID copies of this. We just discussed longitudinal data structure. And we consider some total time points around 7 for at the weeks 3, 6, 12 to 36, because those are the registered designed by the trial, the visits and the lab testing of each of the patients. And for baseline, we have a list of their predicted baseline covariates, and the treatment will be randomized at the baseline. And we allow right censoring for the survival event, and we combine the censoring process into this intervention node, so that we will have the same G-computation formula and the efficient inference function. So we only need to be careful that we also want to multiply by the censoring score when we calculate the propensity score. And for the mediator of interest, it's the blood sugar in HbA1c. So it is fully time varying now. And we can also include all the simultaneous lab testing at the same visits as time varying covariates before the mediator in the RT node. And we can even include other event process of interest in the LT time varying covariate node after the mediator. So our primary outcome interest here is the event process of MACE. So it's the major cardiovascular event, consists of 3 subtypes. Okay, so what is the causal question we will be interested in? So we want to see to what extent is our treatment effect on the survival probability at each of the time point can be mediated by the longitudinal procedure of blood sugar levels. So we can have all these possible causal targets, and we can so because of the randomization of the baseline treatment, we just additionally need our causal structure model assumption, our censoring, ignorability, and the mediator randomization assumptions, and also the positivity assumptions. And then we can get all these targets fully identified, and we will be able to use TME to get efficient estimations and inference. For our estimation procedure, the plan is that we want to use superlearners for the conditional densities at the initial estimation. For binary outcome, also for binary variables, we can always include highly adaptive lasso. And with all the other algorithm candidates like lasso or elastic net or like a random forest or anything. And then for categorical variable, we can use a wrapper called the pooled hazard. So those can be worked out and optimized as linear combination of the learners in superlearner, or we can use discrete learner. So we just choose one of them, which perform the best in the validation set. And then for continuous variables, we can use the recently developed Hall-Densify package or the Condensier package. These are all the packages developed by our group. Can be directly applied for the setting of our problem. And then we can, after we get this initial estimation, we can get our one-step TMLE update using our highly adaptive lasso projected efficient function. And what the density version, the maximum likelihood version of TMLE allows us to do now is that we can be really flexible about what we want to target for our problem. If we want to target the full survival curve, we want to consider the competing risk problems, we can just target multiple targets of interest. To do that, the only thing we need to do is just to include more parameters in our parametric submodels, make it multivariate, and target multiple targets at the same time. And in the end, the statistical inference can be based on either Volt test with the asymptotic results, or can be based on non-parametric bootstrapping if high-level data lasso is the only initial estimator that we use. So hopefully we can get the real data analysis out really soon in the next couple of weeks. But for today's talk, here's a summary. We proposed several different versions of maximum likelihood-based TMLE for the longitudinal causal median question. Just as any other TMLE, they are substitution-based, meaning that they will respect parameter space, which is very crucial for the finite sample performance, and also the interpretability of the final result. At the same time, the R method now is fully density-based, so it can be really flexible if we want to work with different types of causal targets of interest, like survival curve or competing risks. And we can have a guaranteed consistency and the efficiency for the TMLE estimation if we always include highly adaptive lasso in the density estimators. And because of its maximum likelihood now, everything will be fully compatible with the existing TME toolbox, especially the higher order TMLE that is possible to further increase the efficiency of the final inference. And the last variation we proposed is to use the computerized efficient inference function calculation so that we can reduce computational cost and make it more stable and more scalable. So this idea will be naturally combined with the idea of higher order TMLE. So in the end, we should be able to get some fully automated higher order efficient estimation. So that's the next steps we're going to do. Okay, I'll stop here.
Thank you. Let's see, I'll just stop it. Yeah, perfect.
Yeah.
Thank you. Now it's actually time for the Q&A. I have several questions, but I will not misuse. No, actually, I will misuse it a little bit, and have the first question. But I would like to invite everybody to pose questions. It could be in the chat where you write the question. You could just write an X in the chat, I guess, and then we could also offer the word to you, so you can sort of say it yourself. That would also be fine. But now I will hug the opportunity to ask a question, and that is. It's to the last presentation, to say, I was just thinking if we are in some sense being overly flexible. Of course, there's a risk that I misunderstood one of the steps, but it seemed to me like, are we not? How much information are we borrowing from adjacent or closely in time spaced measurements and their effect on the sort of the measurement of the outcome process, etc. Because it would seem biologically plausible that they are probably not the same, but they are somewhat similar, that you don't want to treat them as unrelated or starting from a blank slate, if that makes sense. Maybe I misunderstood something.
Yeah, I think that's a reasonable argument. So if I understood it correctly, that in many scenarios, the sequential regression should just work and should be enough to answer our question of interest. And actually, in terms of their asymptotic properties, the sequential regression version and the density-based version should be equivalent. in the scenarios where they both work. And then what we found, the density version can provide extra opportunity is that for many scenarios, if the final target of interest is not only a conditional mean, but some multivariate process or some, like in the scenario with competing risk with different sub-distributions, it can be not only a simple conditional mean. In those scenarios, the sequential regression might not be able to work out the question. That's one thing, that's one opportunity. And the other opportunity we have been seeing is that even if the estimation has the same properties, their inference will be based on the estimation of our efficient inference function. So for those estimations, we will have some opportunities to reduce our estimation, so to increase our testing power when we switch our conditional mean to the very careful conditional density estimations. Because of the reason we mentioned, possibly because of the reason we mentioned that the sequential regressions are defined in a way that we start with the last time point, where in reality might be the place we have the most severe censoring and missing data issue. Okay, so those are the two possible reasons we might still be interested in the density-based versions, even though the sequential regression version is already really powerful and also equally meaningful.
Yes, thank you. There are two questions in the chat. The first one is to Søren, and it's from a self-declared clinical epidemiologist, and it reads, did I get it right that the analysis indicated that the drug effect was better the less body weight the patient lost during the treatment? So very specific. Søren, are you there?
Yeah. So the question is, the drug effect was better the less body weight the patient lost during the treatments. I'm not quite sure I understand this question.
Torkild, maybe would you like to put a few more words on it? Now you turned on the video, so that's sort of an indication.
Yeah, sorry if I was unclear. Now I don't know what happens. So you indicated that there was no mediating or even opposite mediating effects.
Yeah.
Body weight changes.
Yes,
when you compare the drug with the placebo.
Yeah, that is true.
So what do you mean by that? I mean, I'm just trying to interpret this this claim, but I may have misunderstood it. But I thought it was very interesting because out in the clinical world, it means a lot. What is happening to the body weight changes and what?
Yeah, that is you can say it originates in the question about what is actually negative mediation in a randomized clinical trial.
Yeah,
and it sometimes it appears. First of all, I would say that the negative mediation for body weight, that was apparent in, you can say, in the more naive approach, but it disappeared when we did it properly, you could say. So that should be, of course, be kept in mind. But with regards to negative mediation, it sometimes could be that even though the randomized treatment has you can say a positive effect on the outcome, but it could also sort of influence the mediator in a bad way. That could be that if a drug actually influenced a mediator that would be negative to the outcome, then it could be negative. But I'm not sure that this is the reason why we see this for body weight. And I think it's more, you can say, some data issues in the naive or simple approach.
Yeah, sorry, it was a very specific question, but I think it's very relevant for those of us who want to understand and use the mediation analysis, not least when aiming at translation into kind of real world ideas about what to do with the patients. So thank you for explaining.
Talking. Thank you, Talk. I think this actually cuts very well into one of these communication issues we have, that I think it can be very hard to communicate that we are in some sense not exploring what the mediator does. We are exploring only the totality of the exposure and the mediator, and that can give some pretty weird surprising results, in not least is in this situation that Søren mentioned. If some of the signs are opposite, you really have to be careful. Maya, you had a question? You are muted, Maya.
Yeah, can you hear me now? Yep.
Yes.
Yes, thanks all for a really wonderful series of talks. I was thinking, it's a bit of a question, a bit of a comment back to Thijs's point early on that, there's deep complexities in the types of data, the types of confounding, the analytics that are necessary to handle them appropriately, and yet the impact will be through making it usable. And you showed your kind of one line of code to call things. So I have a bit of a comment and also a question, which I think my comment is that I just want to second that point, and I think that's absolutely right. And I think that's a very achievable goal. I mean, I think even for we've kind of opened the box and seen some of the complexities inside, but even for the most complex methods, to end up at a point where essentially you're guided through a roadmap to indicate, okay, this is the type of data I have. Yes, my treatment, my exposure is at a single time point and it's randomized. My mediator is this, to really be guided through entering that type of data and that type of information. And then really indeed to have a one line of code that will then spit something out, where then also on the output you're guided through maybe interpretation along the lines of what you're saying as well, Torkild. Like, look, this is what this means in words. This is what this number means in words for what you put in, and these are some of the assumptions. And so that's just a comment that I really strongly agree with you, Thijs. And I think it's something we can and should hold ourselves to, and we're increasingly seeing, I think, come out of some of the new developments, but obviously first you have to work out the back end. And so then maybe the question, a long-winded way of asking a question is to Zei, seeing, the beautiful work you presented, how far away do you think it would be to have a front-end version where you really can, for at least, using defaults, essentially put in a few lines of code to get out kind of the 3-line answer of total effect, mediated effect, or indirect effect, direct effect, total effect. Just sort of your take on that. And also anyone else, all of the other speakers, kind of where do you think we are as a field in that? And that's not me, by the way.
Zei, you want to have first go?
Sure. I can go first. We are not there yet, but I think my feeling is that we are getting closer to a place where we can just define our DAG or some generalized DAG, allowing possible unobserved confoundings. And as long as we get the G formula, and we might be able to get a fully automated efficient estimation process, so handle all the rest of the estimation problem. And then only by this type of computerized estimation procedure, we can make it really just let the user to work with the front end, just work with the general causal road mapping part, and then we work out the rest in the black box, and that in the end, we give very careful description. But there is still a long way to go, but I'm seeing a possibility there with the recent development.
That is great news. because I do think that a lot of people would get scared. It looks complicated in implementation. Søren, I know that the fence-aligned methods is not, as I recall it, super easy to implement either, and doesn't have like a flying package, as I recall. Have you some thoughts on Maya's question?
No, I mean, so I think using the SAS package, it is quite you can say easy to implement the mediation analysis I presented, but of course it should be. I mean. For our trials, we have seen this high variability in the analysis. So perhaps it's hard to get some firm conclusions on the variables actually we actually use as mediators. I don't know if that.
I guess I was more concerned about sort of the complexity in implementing the methods. Say that you had a structure-wise similar problem, but otherwise totally unrelated to your study. Would it be possible? How much work would it take to implement it in a new study if you were just reading your paper?
I think it's quite straightforward to use the SAS macro in other setups. You can say that is quite straightforward. I would say.
That is good.
I mean, if you're used to SAS and the macro, then it is quite straightforward. I mean, we see problems sometimes with the bootstrap, for example, that this data it becomes, you can say, very sparse quickly, such that we cannot estimate confidence intervals. So, and that is of course you can say a problem, that you cannot say something firm about the variability in your estimates.
No, yeah, and I guess to some extent that's more of a problem of that's just a limitation of the data more than anything. I guess my comment.
To some
yeah.
Sorry to interrupt. To some extent, a limitation of the data, but also I think a call for methods that both get as much out of the data we have as possible, so we're fully efficient, and also have the give us kind of the tightest confidence intervals that are still reliable, essentially. So I think it is a data issue, but also a call for why perhaps there is a reason to want more complex inside black box or whatever, if you will.
Yeah. Right, I agree. I guess my comment to your original question, Maya, that would be that I think that the roadmap itself would have been a great idea to implement within the studies that I presented, and that is very close to being exactly where it needs to be. That's just something we need to bring out there. Whilst some of the collaborators that I had in those studies, they would still be struggling with the coding issue. That would be sort of rather hammering the squared peg through the round hole than starting much earlier, implement more on their own. So there's also a question from Jesper Madsen to Zay. I'm pretty sure I think I know the answer. So, but the question is the definition of the counterfactual in the URL analysis of the leader data. Is that going to be? Will that have the same interpretation as using the Stein-Fensterlin method? My guess is yes, as far as I understand it, but maybe I was wrong. So what do you say?
I need to look into it more carefully, but my impression is that they are quite the same, but there can be some very subtle differences in the way that we identify the final G formula, in the sense that so they can be the same, but they can also be different one with the more general framework if we allow all the time varying covariates to enter in each of the conditional likelihood to fully adjust all the possible time varying confounding. But maybe I remembered. So what I remember is the Soren's paper is that it kind of simplified some part of the likelihood factor so that they are depending on the baseline covariance. So it's kind of like a conditional version rather than the full version for the marginal based on the baseline. It's a marginal version for the most general possible way to identify the result. There has been some arguments in terms of whether that can be applied to the survival setting, but I think there's some argument, very good, solid argument given in the Soren's paper. So yeah, they can be the same, but they can also be different for some scenarios.
And to clarify a bit, when you're talking about the conditional and both versus marginal, you're talking about specifically what, if you think about the intervention on the mediator as a random intervention or a stochastic intervention, exactly what distribution it's coming from. Is that right? Just to clarify, you're talking about the subtle differences.
Okay. Yes, exactly. Yeah, those very subtle differences in the conditional likelihood.
In some sense, I think this also highlights one of the strengths with the causal roadmap approach, and indeed our approach to causal inference, that we do the separation, and so we can actually have something that is quite close to the same estimate, but with quite different underlying assumptions and underlying modeling assumptions. So it's, yeah. And of course, I still hope that we can probably beat down the standard errors a bit compared to the Stein methods. Any final questions? Then it's about time. Otherwise, we are approaching end of business hours in Denmark. So I would like to remind everybody that we have the next webinar on the 5th of May, which I look much forward to. And then I would just end up by saying thank you to all of you for participating in the questions, discussions, etc. And just have a great day.